And greetings, everyone. Welcome to another episode of Physical AI, powered by Digital, where artificial intelligence meets the real world. And together with brilliant minds, together Peter Stone, we interview founder scientists to explore a couple of things: machine learning and human behavior that converge in space. Peter, how are you today?
I'm doing great. How are you?
Excellent. Thank you so much for taking the time. For those who don't know Peter, allow me here to introduce real quick. Peter, Professor of Computer Science at UT Austin and Chief Scientist at Sony AI, leading pioneering work in autonomous agents, multi-agent system, and reinforced learning. 400 plus publication, roughly 40K citations. Peter's work defines how AI agents learn, plan, coordinate, and act in dynamical world. Former president of IGCAI and co-founder of Cogit AI. He helped advance foundational techniques in continual learning, robotic soccer, autonomous bidding agents, and social robots. At Sony AI, he has driven major breakthrough in responsible human-centric AI, including recent Nature papers at fairness, consent-driven datasets, and real-world vision benchmark. What a amazing opportunity we have here to chat with you and truly pick your brain on some of these subjects, Peter. You ready to kick off things?
I'm ready.
Right on. So I've been working with your former student, Joshua Hanna, to bridge the sim to real gap successfully and to learn the fastest walk on now humanoid robot at that time. So really curious to understand what was here the key that brought you to this success, Peter?
Yeah, thanks for asking. So the now humanoid robot is, for those of you who aren't familiar, it's sort of it's a small humanoid. It comes up to maybe your knee or so. So it's not like a full size humanoid. But it's a very well designed robot. It was designed by a company originally called Aldebaran, and then which was bought by SoftBank. And it was a robot that has been used for many years as the standard platform in the RoboCup competitions, the Robot Soccer World Cup, where the goal is by the year 2050 to have a team of humanoid robots that can beat the best World Cup soccer team on a real soccer field. And as you might imagine, if you're trying to get robots to play soccer, you're pretty incentivized to get them to walk quickly, to move as fast as possible. So there were people around the world trying to not just use the API that comes with the robot, but to try to really get down to the joint motor control to try to get the robots to walk as fast as possible. And my team at UT Austin, called UT Austin Villa, was one of those. And we happened to have a team also that had been very, very successful in a simulation league of RoboCup. So this is one where we were using robots that were modeled loosely after the Now robot, but weren't perfect physical simulations of the Now. So there's actually, and we had been winning that competition. In fact, over the course of 11 years, we won the simulation league, 10 years of those 11. So, and the key was that we were using machine learning to learn a really fast walk and kick and other skills on this simulated robot. But because the simulator was not the same as the real robots, we weren't able to just directly take what we learned on the simulator and use it on the real robots. And that was very frustrating because we had the fastest walk in simulation. Why can't we get this to work on the real robot? And the reason that it just doesn't work out of the box, as many people know, is something called the reality gap, or the sim to real gap, the difference between the simulator and the real robots. And fundamentally, what happens is that when you tell in the simulator a joint to move, to a particular angle, like 90 degrees or something, that it doesn't get all the way there immediately. There's like a PID controller underneath, and so it might, if you have a 180-degree joint and you tell it to go to 90 degrees in the simulator, it might go to 100 degrees or something like that. But in the real world, if you sent that same joint command, the robot is a little different than the simulator. It might go to 100 degrees or 110 degrees. And so what we did is there's basically fundamentally two different ways two classes of methods for bridging the sim to real gap. One of them is some people call domain randomization, which is deliberately make your simulator worse or more noisy, to make it so that the behaviors that you learn are robust to noisy simulations. And with the idea that you hope that the real world will sort of be reflective of that. But the other way, which is what we did, and that what Josiah introduced, was a method called grounded action transformation, which was going the other direction, trying to use data from the real world to make the simulator more reflective of the real world. Not to make it a perfect simulator, but to make it more sort of grounded in reality. And so an important feature of our method was that we could treat the simulator as a black box. We didn't actually change the simulator. Instead, we put a wrapper around the simulator such that every time we would send a command, say this 180-degree joint, if we said to go to 90 degrees, we would first ask, if we say to go to 90 degrees, where will it actually go in the real world? So, like, say that's 100, and it'll go to 100 degrees or something like that. And then so that's sort of a forwards dynamics model. It's saying if we send a command, what will actually happen? And then we said, if we wanted to go to 100 degrees in the simulator, what command would we need to send? This is sort of an inverse dynamics model. And by composing the two of those, we would then change it. Every time our policy would output a command to a joint, we would run it through these two functions and say, let's pretend that the simulator was we were sending to the simulator the angle that will actually make it go to the right place in the real world. And so it's sort of a grounding function. And then we'd relearn the policy in the simulator. And it turned out by doing this iteratively, so we would first have a policy, run it in the real world, make the simulator closer, learn in the simulator, get a new policy, run that in the real world, and then get more grounding data to make the simulator closer to that. We would go through iterations like that. And by doing that, we ended up getting the robot to walk faster than anybody had been able to get to walk. We started with a walk that had been created by some colleagues of ours at University of New South Wales, another RoboCup participant team that was one of the fastest walks at the time. And then by going through this process of grounded simulation learning through a couple of iterations, we were able to speed up the walk by about 40%. And that was the fastest that anybody had been able to make it happen. So
that's very
that's
impressive.
the method. Thanks.
And so in terms of content, I mean, obviously, when we say reinforcement learning and grounded learning, right, you need quite some amount of data. Would you say that it was quite a longer period of time that you collected data, like in order to truly achieve that?
No, so this is the beautiful thing, is that it used a lot of data in the simulator. We were doing reinforcement learning in the simulator, and so that would be sort of an overnight process in the simulator. But the amount of data we took in the real world was just it was a very, very small amount. Like we'd have the robot walk maybe 10 times or something like that. So it would take a few minutes of data in the real world to do the grounding, and then we could send back and do most of the data, most of the computation in the simulation. And there was no way we could get all the data we would have needed in the real world to do the learning, and that's the need, the value or the need for the simulator. But we were able to, by making the simulator be sort of iteratively more reflective of the real world, we were able to take all that data in simulation and then just a small amount, a very manageable amount of data in the real world.
And you said it was the fastest. What speed did you achieve, Peter?
Well, the now is it's not like a running robot. It's not like a cheetah. I can't, I think it was, there's videos on my website. If you look up on ground, you can see the starting walk and you can see the ending walk. If you look up a talk called, I think grounded action transformation for sim to real. And if I remember correctly, it was somewhere in the 24 to 30 centimeter per second range, but it wasn't, so it's not like it's not running faster than people, but this is a sort of a small robot. It's fast for its abilities.
And the project is still on. You mentioned 2050 to play against human beings. Is this still on?
Yeah. So RoboCup as an initiative it's a worldwide initiative. There's people. There's every year there's a competition. There's thousands of people that come. And yeah, the last one was this past summer in Brazil. The next one is this coming summer in Korea. And we're aiming to, and it's not just about robot soccer. Actually, there's also general purpose service robots, rescue robots. But the original impetus for it was this grand challenge of trying to get humanoid robots that can beat the best World Cup team by the year 2050. And yeah, absolutely, it's a very vibrant and active community.
Yeah, I can see that. I mean, now also, I mean, World Cup soccer in general in the United States is growing, right, drastically, right? So very, very intriguing. And now having the mix between the robots that are fast, contextual aware, and intelligent, that'll make a fun game. You mentioned Brazil, right? Obviously, a huge a team, right? A very strong team, right? In the World Cup, that would be really fun to see,
Yep.
right? And so, yeah, let's switch gears. So another recent achievement of yours, you demonstrated successful imitation learning from a single video demonstration that's robust to change camera angles, right? Not just that, but also lighting conditions, object starting positions, and object instances, right? So tell us a bit about what made it possible, Peter.
Yeah, and so this is joint work with a student Yifeng Zhu, who's since then got his PhD, and also his co-advisor UK Zhu, who's also a faculty member here at UT Austin. And the the name of the system is called Orion, and this is so unlike what I was talking about before, which is was machine learning for locomotion, for walking. This system was for manipulation, robots, sort of dexterous manipulation, being able to pick up objects and things like that. And there had been this is the kind of thing where you don't want to just do random exploration reinforcement learning. To move an arm around randomly until it happens to pick something up is never going to happen. And so there's a lot of work in this area to try to base it on either a small number of demonstrations, or watching a person teleoperating a robot to show how you do it and then try to mimic that. But typically, it's required that the camera be sort of in a fixed location for the demonstration, and also for the execution, and that the lighting stays the same, and all those kinds of things. And so our the insight in this work was to use a single video demonstration where what's being captured from the demonstration is not the actual joint angles that the arm needs to move in, but rather the sequence of contact relations between the hand and the objects. So, for example, if the task was to pick up the iPod case and put it on the iPhone, we would get a single demonstration that would basically start with the hand not touching. Then it would say, okay, now the thumb and the forefinger are both touching this object. Then everything's in contact with each other. Then the hand's not in contact, and sort of use this object-centric representation, and not any of the actual joint motions, or not even the actual appearances of the objects, so that you could you could say in a new setting, it could be looking for an iPad case and a phone that look entirely different, that is starting in different locations, and it would try to mimic the sequence of contact relations that we went through in the demonstration. And so because of that, it's not sensitive to the particular details of where the demonstration was. What you're basically getting from this demonstration is the plan, or the plan for the object and manipulator contacts. And this worked very effectively. We were able to show that, if a person demonstrated picking up a mug and putting it on a coaster, even if that mug was black, then we would show a new mug that was pink. The robot would be able to find the mug in the image that was, even though it looked different, go and pick it up and put it on the coaster. We could also do multi-step things where you had to pick up multiple things and stack them on top of each other, so it wasn't sensitive to how long or how many steps were in the plan. And so it was sort of very in contrast to people who are sort of trying to get lots and lots and lots of demonstrations and then sort of summarize them into sort of an abstract representation. We took the view of, we want to get a single demonstration and milk as much information out of it as we possibly can, and make it as sort of lead to a behavior that's as robust and as general as possible. And yeah, so this is something that we originally did it with where the demonstration required RGB and depth, RGBD videos. We've since abstracted it so that we can just deal with RGB videos, which means that now we can use demonstrations that just come straight from the internet, from YouTube or something like that, and have a robot try to mimic them. And so, yeah, this was a fun project.
So what was the common denominator then to make sure that the actual planning went accordingly? Is it the size of the object? Is it the vicinity to the object? Like, because actually you keep on hearing always the opposite to what you're describing. You say one video, right, and then focus on a series of details, right, that
Yeah.
complete an entire job to be done from A to Z, right? But so what was the common denominator
The
here?
common denominator, so, and this is something I've left out to this point, so it's a good point. It's the semantic label of the object. So in addition to the video, we would also give the text string of what it is you would need to pay attention to in the video. So like in this case, we would show the video and then also say iPad case and iPhone. And then using off-the-shelf vision language models and point trackers and hand trackers, and then we would be able to segment out what happens to the iPad case and the phone and the hand during the demonstration. And then when you're given the new scenario, it'll look in an image and look for anything with the semantic label of a phone and an iPad case, or an iPod case, and then it would sort of back project the sequence of motions from the demonstration video onto this new video scenario. And so it's not magic. There has to be some information that ties them together, the common denominator, like you said. And so it's the ability of these vision language models to be able to identify objects from different camera angles, different backgrounds, different, that all have the same semantic label. You can find mugs no matter what they look like, or you can find coasters no matter what they look like, or forks or spoons or phones or whatever, and they all so it's the semantic label and then these contact relations that characterize the demonstration.
And the actual touch point between the object and the case was just one specific verb, right? So it was just stacking, you mentioned, right? So in example,
so we wouldn't even give this, that would be detected from the image. So we basically from the demonstration. So if right now there's the the hand touching the iPod case and the phone, and then now there's the iPod case on top of the phone. That would be automatically extracted. This sort of on top of relationship, the object centric representation would, and there was things represented like part of relations, like the thumb and the finger are part of the hand. If there were objects that had multiple parts, those part of relationships would be represented, but then also on top, sort of relations like next to, on top of, underneath, those would be automatically extracted from the demonstration video.
And that has also a huge impact on compute power, because if we are using just one video, right, it expedites the entire experience, right, expedites the learning, right, and reduces actually the cost of. Do you have any concrete applications already that were built up on it, or was it just an academic level?
So far, this is an academic style thing. That I think we've. There's some videos that go along. If you find the Orion webpage, we show videos of it working on a robot, and so I think, but it's still not. This was more proof of concept. There are still failures. If you look in the paper, it's not 100% successful. Most of the failures were actually in the tracking parts of things, not in the mimicking the demonstration side of things. But we think it has a lot of potential for applications.
Absolutely, 100%. Yeah, congratulations on that work. So sticking to still robotics here, you used recently a low-fidelity simulator to learn an appropriate action abstraction to enable learning downstream tasks, right, with very low, simple complexity. So how did you do that?
Yeah. So, and this is now, I talked about locomotion, and then I talked about manipulation. But now this is in a setting of mobile manipulation, where we have a robot that's on in this case on wheels that also has an arm. And our goal there, this is joint work with the main student on the work is Jiaheng Hu, and it's also joint work with his co-advisor Roberto Martin. And this is work that was recently published in the Coral Conference on Robot Learning, called SLAC, SLAC. And the idea is that we wanted to allow the mobile manipulation robot to now not do imitation learning, but actually do reinforcement learning. So trying to do exploration to get tasks done where all of the data was in the real world. So now no simulator, because if you have whereas the first thing I talked about was bridging the sim to real gap. It's not always possible to bridge the sim to real gap. And so sometimes you want to do your learning on the real hardware itself. But if you're going to do that, as you mentioned earlier, data is important. You can't have tons and tons of experiences on a real robot. And so the insight in this work was to use a low fidelity simulator to have a robot sort of explore a task and learn a very low dimensional action space, so that there was sort of some efficiency in trying to figure out what parts of the world can you ignore, what are the sort of modalities of actions that might be useful for the task, so that when you get to the real world, you're not randomly exploring a huge, enormous space, but rather a much more constrained space, such that within like an hour or so of a robot just starting from no behavior, was able to learn things like wiping a whiteboard with an eraser, or sweeping material off of garbage off of a table into a dustbin. And where really literally all the learning of these behaviors happened in the real world on the real robot. And the key to it was this, first exploring the task, not to learn the behavior in the simulator, but to learn this more compact, abstract representation that would make learning in the real world tractable.
Very intriguing, very compelling. Peter, leave our audience with your 2, 3, 4, 5 years. I know it's right now it's a lot of things that can happen, but leave our audience with your vision on what breakthroughs do you see that need to happen in physical AI in order for us to leverage through an augmented physical world with the intelligence of AI. What are your thoughts there?
I mean, I'm really excited about sort of the confluence of some of the newest methods that are becoming possible with with visual language models and visual action models, but in coordination and confluence with more classical robotics and classical AI and planning. And I think that there are people who are sort of sticking to the old-fashioned or classical way of doing things. There are people who are throwing away all of the old-fashioned classical way of doing things and trying to do everything with data and visual language action models. I actually think the sweet spot is going to be right in the middle, where we're identifying exactly where foundation models can and should be used, especially for common sense knowledge about the world, for where to search, for high-level task planning, but still use PID controllers and model predictive control and sort of some of the classical, even some classical path planning algorithms as the substrate, as the to build upon. And I think we still haven't figured out as a community where the right interface is between those and how to mix them appropriately. And so I think over the next several years, we're going to start sort of seeing best practices and emerge as to what can we do with what's going to be the role of data and experience, what's going to be the role of models and sort of computation, and how can they be unified.
No, I love that. Yes, absolutely. Not just do we need to understand the geometrics and the semantics and the contextual world, right? But then actually the actions, right? Which in large language models are, let's say, linearly with the 2T tokens. It's a more tangible way of understanding and processing data, right? But in the real world, how do we empower machines, and then how can the users and us, humanity, benefit from that? Not just by having robots and autonomous systems, but also through immersive worlds, right? For our audience, please join our Physical AI Symposium in Silicon Valley, 23rd of April. If you are interested about this topic about physical AI, click here on the link or scan the QR code. Super excited about that. And how can people read more about what you're working on, Peter? What can you share with us so we can add it to the show here?
Yeah, if you search for my website, Peter Stone, UT Austin, I've got all of my publications are there. And what I would especially recommend, if you prefer learning from videos, if you click on the button Courses and Talks and then scroll past my courses, you see a whole bunch of online talks, and the titles are pretty descriptive. Some of them about the details of what I've, some more details of the things I've been talking about today, and then some completely different topics as well. So, and if anybody has questions about the work, I invite them to reach out to me by email.
Peter Stone, awesome. Thank you so much for your time, and I'll see you in the metaphysical world. All right. Bye.
Thank you.
Bye.